Add the following two binary numbers using 4-bit, 1's complement and 2's complement. So let's just review. First, A, we have what? -1 and -7. Using 1's complement. Finding negative numbers, I don't know in your 312, probably you talked about 3 different ways to put it in the negative numbers, but in our class in 145, only 2, 1's complement and 2's complement. So to get to negative number, we need to work on positive first and then turn that into 1's complement or 2's complement. So positive 1 is 0, 0, 0, 1, because it's a 4-bit number. And then using 1's complement, flip the bits, 1, 1, 1, 0. And for the 7, we need to work on the positive 7, 0, 1, 1, 1. And then flip the bits, 1, 0, 0, 0. Now we need to add. That's the 1's complement. So let's add. 0 plus 0 is what?
0.
Thank you. 1 plus 0, 1. 1 plus 0, 1. 1 plus 1.
0.
Thank you. Before somebody said 2. We have a carry. What do we do when we have a carry in 1's complement notation?
Would we add it?
Exactly. Bring it down, add it, 1, 1, 1, 0. And if you convert this into decimal number, positive, because it starts with the 0, which is positive, and 1, 2, 4. 4 plus 2 plus 1, which is 7. We have -1, negative number plus negative number, and we have a positive number. No way, Jose, right? So it's overflow. And now, using 2's complement, -1, reading from left to the right, underline the last one, and flip 1, 1, 1, 1. Left to the right, underline the last one, flip 1, 0, 0, 1, and add. 1 plus 1, 0, carry 1. 1 plus 0 plus 1, 0, carry 1. 1 plus 0 plus 1, 0, carry 1. 1 plus 1 plus 1, 1, and carry. For 2's complement notation, for addition, if there is a carry, we simply ignore. And what is this in decimal? Exactly, -8, not +8. Okay, because start with the 1, okay, it's a negative. So as you can see, 2's complement, we can go down to -8, so there's no overflow. And if we have a, more than -8, I mean, it's going to be overflow. Right? And for the 1's complement, we can go up to -7. There's no -8 in the 1's complement. Okay, 2 and -2. So we have 2, 0, 0, 1, 0, -2, 1, 1, 0, 1, and add 1, 1, 1, 1. What is this in decimal? Convert it. Use in your notes. Try to convert this binary number into decimal. So as a 1's complement notation, it's a negative. So in order to find equivalent decimal number, what we need to do, we need to flip the bit. Before we flip the bit, it is a negative, right? Because start with the 1, right? So I'm going to put negative and flip the bit, 0, 0, 0, 0, which is -0 in decimal. There is no such a thing as a -0, but in 1's complement, we do. If you're using 2's complement, we have 0, 0, 1, 0, and then you can read from left to the right, underline the last one, and flip the bit. 1, 1, 1, 0. So this is -2 under the 2's complement notation. And then add 0, 0, 0, 0, 1 carry. We ignore the carry, and this is 0 in decimal. When you say it's a negative number in this class in 451, we're using 2's complement only. For this chapter 5 is about the digital building block. I mean, in the 312, we talk about the gates, multiplexers, decoders, registers, all of those. You will see some of those again later. So you can take a look at this. Then the first arithmetic circuit is adder. I mean, this is from 312. You don't have to copy this down. And the major difference between the half adder and full adder. Anybody knows what's the difference between the half adder and full adder? Look the same, right? So half adder, there are only 2 inputs. Full adders, 3 inputs. In the diagram, there is no carry in. Full adder, we have to have a carry in. Any adder we have is using the full adders. So this is half adder and full adders, and there are more adders. So ripple carry and carry look ahead. I'm not going to, I just show you the diagram, and you don't have to worry about these two. So ripple carry, so you have the bits. If it's we have a 32, bit 2 registers, you're gonna add them up, lowest bit, put it in, put it in, put it in. But these guys cannot calculate until we know about the carrier, right? So that's why it's a ripple carry. Adder is a slow because we have to add from here and then see whether we have a carry here or not, and then add carry or not, add carry or not, add carry or not. So we cannot do it at the same time. So here's another one, carry look ahead. And if you just put those into logic diagram, and there is somehow without this carry, C is the carry bit, and A and B is just, the C means this carry bit. And so A plus B, each bit we're gonna call it P, and then we keep adding separately. Then what's gonna happen is later portion, I did all of those, but later portion, carry bit 3 is, carry bit 3 means third one in here. In that equation, if you see it, carry bit 3 here, we don't have to know carry bit 1 or 2, only carry 0. Based on this circuit, if we know the first carry, if you keep expanding this equation, then we don't have to wait until C1, C2, C3, C4, all the way to C32. We don't need to wait. Just, it's going to be really complicated equations, but finding the third carry, we don't need to know second and first. That means finding carry 4, C4, we don't have to know C3, C2, C1. Right? So you can expand it. But that's what we call carry look ahead the diagram, and carry look at diagram and can be implemented using this AND gates, OR gates, all of this. And we have a subtractor. And actually, in the computer architecture, there is no subtraction. We have a instruction, but basically the subtraction is adding the first number and the 2's complement of the second number, right? Just what we did. We add 2 numbers. If it is a subtraction, for example, in here, 7 minus 4, and there's no subtracting hardware. They're always adding. How? 7 plus -4. So as long as we can find 2's complement of -4, which is flip the bit and then add 1, right? Then we can use subtraction using the addition. So that's what it is. Okay? So the NOT gates, and you flip the bit for the second number, and then there's adding 1 from here. So we do that. And competitors. So if you want to compare 2 numbers, we can use these blocks. Okay? So when do we need these competitors? We want to see two numbers are the same or not. So we feed in those 2 numbers in this competitor. The output is 0. That means 2 numbers are the same. And if it's 1, the first number is greater than second number. If it's 0, second number is less than first number. I mean, all of those calculations. In our ARMS architecture, the ALU, it looks like this. And in ALU, we can do addition, subtraction, and AND them. AND means go through the AND gates and then OR them. Okay? So ALU control is going to be 0, 0, 0, 1, 1, 0, 1, 1, and adding, subtracting, ANDing, and ORing. So here's the ALU we can design, and we will use this ALU hardware portion in chapter 7 in the architecture part. So here's the quick example, A or B. For the OR, let's just put A or B. So in this mux, you just need to select 1, 1, this guy input, and then output is going to be ORing it, right? And then all of this, there is calculation waiting here. However, we don't select this as an output. You can control the output based on these two numbers. If you want to add, we have A goes here, and then B, we select 0. Also, we select 0 here, and then add them up, and then we go here and here. But since this is 0 and 0, we select 0 and 0, so there's a addition. Very straightforward. The same way for the subtraction, now we're going to select here, this guy is going to be 1, and then for here, we're going to add them up. But when you add, because we select 1, we're going to feed it 1. So flipping the bit plus 1. So here is a 1's complement, adding 1, making 2's complement, and go through here. We produce the subtraction. Caption as ALU with the status flag. Okay, flags, that's the keyword. Flags. We're going to get flags from ALU. So when we fit in two binary numbers, we should be able to get flags for the 4-bit, that 4-bit equivalent to NZCV. Based on this flag, we know those two numbers are the same. If they are the same, we're going to have a Z equals to 1, right? So you also want to write this down. If n equals to 1, what is telling us? We don't know exact binary number for A and B, but if n equals to 1, meaning negative, that means what? B is greater than A, right? 7 minus 4, it's going to be positive, right? Because it is a positive, n equals to 0. It's not. It's not flag up. Hey, this number is negative. That's the flag up. Hey, this number is a 0. That's the flag up. Hey, this number has to carry out. That's the flag up. Hey, there is overflow, flag up. But when n equals to 1, flag up, the result is negative. Therefore, 4 minus 7. Okay, when you do the 4 minus 7, the result is a negative. So it's a negative. Result is 0, then z equals to 1. It's a little bit confusing, but when z equals to 1, that means result is 0. When z equals to 0, result is not 0. It's confusing, but makes sense, right? And then if there's a carry and overflow, I mean, those are the straightforward. Okay. Okay. So this is the whole ALU with everything. You don't have to worry too much about, components, but you need to understand what's going on with the N value, Z value, C value, okay, V, and so on. Shifters, this is important, right? So logic shift to the left and fill space is empty as a 0. Arithmetic shift is a different story, and we have a rotator as well. Copy this down. Logical shifter shifts the value to left or right and fills empty space with the 0. That's the keyword. LSR, LSL. There's an actual, the name of the instruction that we'll see again in chapter 6, chapter 7. Okay. Logically shift right, logically shift left. That's what I mean by that. You will be given any binary number in the register. So all of this ARM architecture for our version is going to be 32-bit. For example, we have a 5 bits. You're given 11001, and we want to logically shift to the right by 2. What's going to happen? Shift to the right by 1, 1, 1, 0, 0. This guy is going to go away. This is the logically shift to the right by 1. Make sense? Now we have empty spot, the most significant MSB bit, empty spot. For the logical shift, okay, we fill with what? 0. So what's going to happen here is, if this was the numbers, it was a negative, now we convert to the positive. So we cannot use this logically shift for actual numbers. But sometimes we need that. Now that's 1. Now we're going to shift it again. 1, 1, 0. And this guy gonna go away. And this. Similar way, logically shift left. Do it. You do it. Okay. The next shifter is called arithmetic shifter. Arithmetic shift to the right, we need to look at the sign of the number. So this arithmetic shift actually can be used for the numbers. We have 11001, same example. Logically shift to the right by 1. So I'm going to shift this guy 1, 1, 0, 0. And this is going to go away. The empty spot here is what? Based on the sign. What was this? It was negative number. How do you know? Because it starts with the 1. That's why it says looking at the most significant bit and copy this down. For the arithmetic shift to the left though, there's no sign matters because shift to the left. So we're lower bits. So this is basically the same as logically shift left by 2. It's exactly the same. Now, rotator. There is a ROL, ROL, rotate to the right, rotate to the left by 2 bits. So when you rotate to the right, you push everything to the right by 2, but anything we lost, we put it back into to the front. So after right by 2-bit, whatever, getting out from the number, putting into the most significant bit. Similar way, rotate to the left, we left by 2, and bring whatever on the most significant bits to the right. That makes sense, right? Rotate within the numbers. Yep. We'll see this again later. This is just a diagram for the shifting technique. We'll see this again. Shift. It's a shift amount. Okay. We see the total number of shift. That means the shift amount. Multipliers. When you multiply 230 times 42 in the decimal number, what we do is lower bit times this whole thing as a 460, and then move 1 bit to the left, and then 4 times 230, and then add, right? So in the binary numbers, we do the same thing. Right? We have to shift every time. But it's not easy to shifting. Okay? It's kind of hard. Instead, what we can do, we can shift one shift to the left, one shift to the right. So let's say you don't have to copy this now. 0, 0, 0, 0, 1, 0, 0, 0. That's the first number, and we want to multiply this. What we're going to do, for the numerator, the first number, we're going to shift every calculus, we're going to shift to the left, and the second one to the shift to the right, so that is the same effect on moving these guys. So we need to multiply this one for whole this, and then this one for whole this, right? There is no mechanism we can ask the computer to read this guy, this guy, this guy, this guy in turn. So instead, we can just read the very bottom, but every time after we read the first number and shift, and then read the second number, shift to read this number. That's how we're going to read through that. And getting the result to the left, that is the effect of shifting this guy, okay, to the left. So the top one to the left, the bottom one to the right. So if we have a 1, this whole thing, we write it. And then we move to the left and right, and it's a 0 times whole thing 0. Move to the left and right again, and this is 0, so we copy 0 down and move to the left and right again. Since this is 1, we copy whole thing down and then add. This is the result. Problem with this is we cannot multiply a negative number. So this multiplier is not working with the negative number. So we have both algorithm. Copy this down. So we're gonna do, when we multiply two numbers, 4 times 7, right, is the same as 7 times 4, right? So when you're given two numbers, it really doesn't matter. You use Q as a 0, 1, 1, 1, get quotient or multiplier, or you use 0, 0, 1, 1 as a quotient. It really doesn't matter. That's the first thing. I use 0, 0, 1, 1 as a Q, 0, 1, 1, 1 as an M. But if you flip those two, result is going to be the same. So for the quiz and exam, I give you Q equals to this, M equals to this. So 0, 0, 1, 1, 0, 1, 1, 1, or 0, 1, 1, 1, 0, 0, 1. That's the first thing. How many bits for the first number? 4. How many bits for the second number? 4. That's why we need 4 iterations. If we have a first number 5 bit, second number 0, 1, 0, 1, 4 bit, then how many iterations? 5. Okay, we need to go with the largest number of bits. So this is 5 bit. And how we make this as a 5 bit? Simply adding 0. So even if I give you this and this, definitely I'll do that. Okay, I'll give you one as 2 bit or 3 bits, one number as a 4 bit, 5 bits, but you need to make the two binary numbers in the equal length number of bits. How? By extended the sign. Because it's a positive, you add the 0. If I give you 0, 1, 0, 0, 1 times 1, 1, 0, this is 5 bit, this is 3 bit, you need to make it this to 5 bit. You cannot make this to 3 bit. That's, you're going to change the number. You are not allowed to do that. But we can change this to 5 bit. How? 2's complement. That's already the negative number, so we don't have to worry about 2's complement, 1's complement. And as I said, if it's a negative number, it's a 2's complement notation. I'm not asking you to change this negative number to decimal number. When do we use 2's complement, 1's complement? When you see the negative number and I want to see in the decimal number. That's the case where you want to apply 2's complement and 1's complement and change it. But if it is a negative number, the computer knows this is a negative number. You start with the 1. Now we need to make this into 5 bit. So for example, let's have this as, since somebody says as 2's complement. Find equivalent decimal number. What is this? How do you know? I don't know. So we need to take the 2's complement. Reading from left to the right, underline the last one, put the negative 0, 1, 0, which is negative 2 in the decimal. Okay? Now, if we have 1, 1, 1, 0, and the 2, let's find out. So the last one is this, negative 0, 0, 1, 0. So this is negative 2. Same. What about 1, 1, 1, 1, 1, 0? What is that? Negative 2. So when we do the arithmetic shift to the right, adding the sign, we are not changing the number. So that is a great way to match up two binary number to equal length. So in this case, what do we do? So we need to do 1, 1, 1, 1, 0, adding 2 ones to the front. So you need to do the 5 iteration. And then I'm going to call this as a iteration. So 0 iteration step init, initial, As a default, if you have 4 and 4, A is going to be all 0 for 4-bit. And then there is what we call Q negative 1-bit. Okay? So this is Q bit, Q0, Q1, Q2, Q3. Okay? For our class, the lowest bit is the 0 bit. Okay? So if you have a 32 bits, the most significant bit is 31st bit because we start with the 0. The right side of the 0 is a negative 1, so we just the booth made it up. Call it as a Q negative 1, and initial number is going to be 0. We okay so far? The whole algorithm is based on Q0 and Q negative 1. So Q0 and Q negative 1, there is a 2 bits if they are the same, 0, 0 or 1, 1. That's the no action case. Just copy down whatever the previous. Right? No action is required. However, if we have a 1, 0 or 0, 1. So those are the 4 different cases with the 2-bit binary number, right? So 0, 0, 0, 1, 1, 0, 1, 1. If you have a 0, 0, 1, 1, they are the same. No action is required. So just copy down. However, if we have a 1, 0, we need to do something. And if we have a 0, 1, we need to do something. 1, 0, leading number is 1 is what? Negative. So in this case, new A is going to be A minus M. And if it's 0, 1, new A is going to be 0 plus M. That's how I remember. It's starting with the 1, it's a negative, so we need to subtract. It start with the 0, it's a positive, we need to add. So it is 1, 0. So in step 1, what we need to do, we need to do A equals to A minus M. We don't do subtraction, right? So what I want to do, I want to have a minus M here, and then I'm going to add. Whenever we need to subtract, I'm going to just add minus M. What's the minus M? Last one is this guy. Flip it, 1, 0, 0, 1. So A minus M is A plus minus M, which is A is 0, 0, 0, 0. M minus M is 1, 0, 0, 1. New number is going to be 1, 0, 0, 1, 0, 0, 1, 1, 0. And for the M side, we don't change. M is there. So you don't have to copy down over and over again. We got always the second step for every iteration. It's going to be shift, arithmetic shift to the right by 1. For this result, shift to the right. So 1, 0, 0, 1, 0, 0, 1, 1. It's arithmetic shift to the right. What do we need to fill in here? 1. And then iteration 2, we need to look at lower 2-bit, 1 and 1. They are the same. No action. Yay. Let's copy down. Arithmetic shift to the right by 1. 1, 1, 0, 0, 1, 0, 0, 1. And we need to fill in 1 again because it's a negative number. Now we'll look at Q0 and Q minus 1. It is 0, 1. So in the 0, 1, we need to add. So A equals A plus M. A is 1 now. 1, 1, 1, 0. M is what? 0, 1, 1, 1. And add 1, 0, carry 1, carry 1, 1, carry 1, 0. Now we have 0, 1, 0, 1, 0, 1, 0, 0, 1. Arithmetic shift right by 1. So 0, 1, 0, 1, 0, 1, 0, 0. And this time, since it's a positive, we need to fit in 0. And the last step, we have 0 and 0, the same number. Yay. No action. Copy down 0, 1, 0, 1, 0, 1, 0, 0. Arithmetic shift to the right by 1. 0, 0, 0, 1, 0. 1, 0, 1, 0. So the result, Q times M equals 0, 0, 0, 1, 0, 1, 0, 1. We have Q7. We have M goes to 3. And the result, 1, 2, 4, 8, 16, which is 21. That is the correct answer.